Let's take a look at propagation of the action potential in a myelinated axon. And we will take an axon that is found in the peripheral nervous system. And as you know, that means that it'll be wrapped with Schwann cells. Actually, let's make the Schwann cells blue. Let's use the color blue to indicate these Schwann cells. And of course, I'm not drawing them extremely well, but I think you get my point. Notice that in between the Schwann cells we have our nodes of Ranvier, and we need to say a couple of things about these nodes of Ranvier. Clearly the nodes of Ranvier are naked areas of axon in between consecutive Schwann cells. But what's more important to know about them is that it's only in these nodes of Ranvier that we find our voltage-gated channels. We have the Schwann cells present in other areas or around other areas of the axon, so we have very little threat of leakage. The Schwann cells, maybe this is not the best way to say it, but literally the Schwann cells prevent too much leakage because they're covering up those. If there were leakage channels, they're covered up. Now, therefore, let's assume that our axon hillock is right here, and our action potential, bang, fires here, and then it recreates itself here. What we then see is that it suddenly leaps, as if it were, all the way to the next node, and again leaps to the node that follows it and recreates itself there. So wherever there are Schwann cells, we don't see any action potentials occurring. The Schwann cells insulate the axon there, and somehow what happens is that the local current is going to carry the depolarization wave that's started by the action potential on the inside of our axon and on the outside of the Schwann cell. This current has to travel quite a ways through the area that is covered by the Schwann cell, but since the Schwann cells prevent leakage, the local current maintains its strength. It doesn't lose much of its strength, and therefore the local current will actually reach threshold level at each node of Ranvier, allowing for these action potentials to recreate themselves from node to node. So if I put a big star by where action potentials are firing, notice that it's as if the action potentials leap from node to node. And we refer to this as saltatory conduction. And saltare in Latin means to jump or to leap. Saltatory conduction. Now, this also occurs in the central nervous system, but recall that in the central nervous system it is the oligodendrocytes that form the myelin sheath. But the principle of saltatory conduction is the same. One other comment to make is the following, and that is, if a disorder of some sorts destroys the myelin sheath in axons, you can imagine that it becomes much more difficult for these axons to leap, and consequently they may not be able to make it at all to those next voltage gated ion groups that are located in the nodes of Ranvier, or once were nodes of Ranvier, and that means that these action potentials can't persist. Or it's possible that with time, new ion gates will develop in the areas where the Schwann cells used to be, or the myelin sheet used to be. And this brings up the concept of multiple sclerosis, or MS. Multiple sclerosis is a disorder that it's a disorder of demyelination in the CNS. So the axons in the CNS are starting to lose the myelin sheath formed by the oligodendrocytes. Therefore, action potentials can either not propagate at all, or they're much slower. As you can see, the presence of the myelin sheath doesn't only provide protection and insulation to the axon, but it allows for the action potential to travel or propagate so much faster. This wraps up our discussion of how action potentials propagate, how they fire, and what they look like on a graph.